Let's say we need to build a length of train track in the Australian outback. Each steel track segment is 25 metres long when it's 25 degrees Celsius and is welded together at each end, effectively producing one long length of steel track. However, if we don't introduce thermal expansion joints like these here, and do this at regular intervals along the length of the track, our track will start to warp as the temperature varies throughout the year. So the question is, if our thermal expansion joints can be no longer than 10 centimetres, what is the maximum length of welded track we can have so that in the hottest times of the year, the expansion gap reduces to 0 centimetres but doesn't overlap and cause warping, and in the coldest months, the gaps don't exceed a distance of 10 centimetres. So let's draw a cross-section of a couple of rail segments so we can visualise this better. So at the very coldest temperatures, the length here of our track segments should be spaced so that the gap is no larger than 10 centimetres. But at the hottest times of the year, these track segments should join up to one long length of track, so there's no gap in between them. Now, the change in length of an object is directly proportional to the change in its temperature and can be expressed with this equation, where the change in length is equal to the average coefficient of linear expansion for this particular material, Li, which is the initial length of the material, and delta T, which is the change in temperature. And for most materials, the length will increase when the temperature increases. But if the temperature decreases, the length will decrease by delta L. In some situations, materials will have a negative average coefficient of linear expansion. So when the temperature increases, the material will contract. And when the temperature decreases, the material will expand. So let's say the coldest ever temperature in this region was recorded to be -2 degrees Celsius, and the hottest temperature at 55 degrees Celsius. If we look back at our diagram, we know that at the coldest temperature, our track segments will have the shortest length possible, but the tracks can't be more than 10 centimetres apart. As the temperature increases by a possible 57 degrees, these tracks will lengthen, but cannot cross the central dividing line. Now, when these track segments are laid out like this, they're allowed to change their length by a maximum of 10 centimetres, and this is our delta L. We also know the maximum range of temperature is 57 degrees Celsius, that's our delta T. And we also know the average linear expansion coefficient for the steel we're using for our track is equal to this value here. And this would have been determined experimentally. All we need to work out now is the maximum length of segment we can use with our current constraints. So we can rearrange this equation and make the initial length here the subject of the formula. We get a value of 160 metres to two significant figures. Ideally, we'd need a more accurate result than this, so we'd need a more accurate value for the change in temperature and a more accurate value for the average linear expansion coefficient. If we have more significant figures in these values, then our final result would be more accurate. But this length represents the maximum length we're allowed at -2 degrees Celsius. If we're laying this track at 25 degrees Celsius, we can work out how much this track would expand with a temperature increase of 27 degrees. And again, we use our formula to work out the change in length, and we get a value of 4.8 centimetres. So our track segments can be nearly 5 centimetres longer and still fit in with our constraints.